Hello friends, welcome to my YouTube channel. My name is Prathmesh. Without wasting our time, let's begin. And if you like, please like, share, and subscribe.
Current AI architecture is strictly reactive. These massive models effectively sit idle in the dark, occupying server space without computing until they receive human instructions. This industry-standard workflow is known as the synchronous loop. The system stays dormant, waiting for a prompt to trigger a session. This diagram shows the mechanics. A user enters a query, the processing node generates the requested text, and the session ends. The process hits a wall. The software cannot proceed to a second step or initiate a follow-up without a new human command. Google is currently testing an internal project codenamed REMY. It is designed to function as a 24/7 personal assistant that manages schedules and information across a user's work and school life. Moving from a reactive chatbot to a continuous assistant requires an asynchronous agentic loop. This new loop replaces the linear path with a rotating circle of operations. There is no single input origin because the system is designed to cycle through tasks without waiting for a prompt to start. Analysts describe REMY as Google's direct technical response to emerging autonomous competitors like OpenClaw. Building this capability depends on three technical pillars: continuous data monitoring, cross-service orchestration, and stateful memory. Google's engineering focus has shifted toward task execution. The goal is no longer the generation of accurate text, but the autonomous completion of multi-step workflows. REMY's first leaked feature is its focus on monitoring. It is designed to track important updates and data changes automatically. However, running a high-parameter language model 24/7 for millions of users is physically impossible due to the massive compute costs and energy requirements. To bypass this bottleneck, the system uses an event-driven architecture. This architecture separates light monitoring from heavy reasoning. SNO listener nodes scan incoming data, letting standard packets pass constantly. A listener activates only when a specific packet hits an importance threshold, sending a direct signal to wake the central model and process the update. This entire sequence occurs without the user typing a single word into a chat box. This framework allows REMY to act in the background, performing digital labor while the user is away from their device. Machine autonomy is achieved through these automated waking mechanisms, which prioritize compute efficiency over constant processing. For the REMY agent to be truly effective in daily workflows, it requires deep, seamless integration across the entire Google Workspace ecosystem. An autonomous reasoning engine cannot complete tasks if it is locked in an isolated window. It needs the ability to read from and write to external software. Google achieves this by positioning the AI as an API orchestration layer. While standard chatbots produce human-readable text, an orchestration layer produces structured code designed for machine execution. The central node bridges services, routing logic to Gmail, Docs, and Sheets. A data packet emerges from Gmail. The AI reformats this unstructured text into a rigid logic block, then writes it directly into the Sheets silo, updating the user's data automatically. This process fulfills the cross-service mandate mentioned in the internal testing leaks. Ecosystem orchestration changes the AI from a simple conversation partner into a system operator. The third engineering requirement is learning user preferences over time to ensure tailored assistance. Standard chatbots suffer from amnesia. Every session is a blank slate with no memory of user preferences. Solving this issue requires stateful, persistent memory. A user vector database runs parallel to the AI core as a permanent memory bank. Logged data fragments flow down and accumulate. When a new task triggers, the AI pauses, querying this persistent memory to match how the user handled similar tasks in the past. By merging the new task with historical data, the AI ensures the final action matches the user's specific style without being told twice. This architecture removes the friction of providing repetitive instructions for routine work. Stateful memory is the technical line that separates a general-purpose tool from a personalized assistant. This is the complete system: event listeners, software silos, and persistent memory looping around the central REMY engine. Google is currently restricting access to this system, testing it only within a staff-only version of the Gemini app. The decision to keep the project internal highlights the stark reality that AI models still make significant errors. In an autonomous system, a simple error becomes an action hallucination. If a chatbot hallucinates, it displays incorrect text. The user simply reads the mistake on their screen. If an agent with write access hallucinates, it executes a mistake within the user's actual files and accounts. A proactive agent could autonomously delete vital emails, send incorrect invites to a professional network, or corrupt financial spreadsheets. Google's internal testing is focused on building mathematical guardrails to ensure the AI cannot take an action that violates user data integrity. The absence of a public release date suggests these safety bottlenecks remain a primary concern for the development team. Granting machines the power to act is now a solved engineering problem. The final hurdle to a public launch is establishing the mathematical reliability required to let them. The most advanced language models operating right now are built like massive, complex industrial engines. No matter how much processing power sits under the hood, those gears wait entirely motionless until you step up and pull the lever. That lever is the user prompt. Standard conversational models are highly effective at answering questions and generating text, but their architecture is strictly reactive. Every single digital action requires a direct manual command to initiate the process. This side-by-side diagram illustrates the architectural shift required to move past that limitation. On the left is the standard reactive LLM. It follows a rigid linear flow. It takes a user prompt, processes the request, delivers a text output, and stops entirely. To execute complex multi-step tasks across different applications, you need the architecture on the right, a large action model, or LAM. The proactive LAM is built to operate continuously. Instead of waiting for a prompt, it reads a digital environment, parses the incoming data, executes an action, and then loops right back to monitoring the environment. It acts without a user command. The industry is moving past generating static text answers. The current objective for tech giants is deploying autonomous systems that can execute complete workflows across multiple services in the background. Google is currently running covert internal testing on a new AI agent designed exactly for this purpose. It operates under the codename Project REMY. The internal design philosophy for REMY frames it as a 24/7 personal assistant. Its specific directive is to autonomously manage a user's work, school, and daily life. Instead of passively waiting in a chat window, REMY is programmed to actively monitor streams of incoming information. If an important update arrives, the agent parses the context and takes proactive action on the user's behalf immediately. Analysts tracking the sector view Google's development of REMY as a necessary strategic counter to independent, action-oriented competitors currently entering the market, like OpenClaw. To understand what actually allows an AI to act autonomously, we need to evaluate the technical logic REMY uses and compare its architectural approach directly against standalone agents like OpenClaw. Designing an agent requires abandoning the generative architecture that powers chatbots and replacing it with an action-oriented framework. Look at this logic tree. In a standard model, the logic path is a straight line to a dead end. The entire operation terminates the exact millisecond the text generation is delivered to the screen. For an agent like REMY, the logic must extend past text and push out into actual digital environments. After executing an action, the agent triggers a feedback loop to confirm the result of what it just did. This requires continuous background state loops. The system maintains a constant pulse, continuously monitoring the environment for new variables, rather than shutting down and waiting to be spoken to. It processes this incoming data through an observe, orient, decide, act loop. The agent observes a change, orients itself to the new context, decides on the optimal response, and acts. When that first action alters the environment, the observation phase begins again immediately. This allows the agent to fire off secondary and tertiary actions in a cascading sequence based strictly on the outcome of the first. Complex task execution relies on constant, uninterrupted background awareness, making the agent's persistence as important as its raw intelligence. Understanding the logic loop is only half the equation. To actually execute an action, like moving a meeting on a calendar, the agent needs the physical infrastructure to reach the data. This diagram maps out the standard Google Workspace ecosystem. Massive amounts of user data are contained within these individual, siloed applications, like Gmail, Docs, and Sheets. To function autonomously, an AI needs unfettered read and write access to all of these data environments at the exact same time. We can place Project REMY at the center of this map because it is built directly into the server architecture. This provides REMY with native permissions. It operates from within the data environment, meaning data transfers between the applications and the AI with zero friction. Deep integration means the agent never has to stop and authenticate its identity when moving between different services. In a live workflow, an email containing an itinerary arrives in Gmail. REMY parses the text, extracts the times, and instantly pushes an update to a schedule in Google Sheets. Because the agent has constant access to these workflows, it continuously logs how you prioritize emails, organize spreadsheets, and format documents. Compiling that behavioral data over time is how the agent builds a highly tailored operational profile, learning to mimic the specific way a user manages their workload. Google's structural advantage over competitors is a native environment completely devoid of digital friction. That lack of friction becomes critical when you look at the wider competitor landscape. Standalone models like OpenClaw are trying to achieve the exact same proactive task execution. This split-screen matrix highlights the architectural divide. On the left, REMY operates inside the ecosystem. On the right, competitors must build generalized models that live completely outside the user's data boundary. Since they lack native permissions, external models must plug into user systems using external API gateways. These are narrow, highly regulated bridges for data. This introduces API friction. When third-party software attempts to read a continuous stream of incoming data, the host servers impose strict rate limits and artificial bottlenecks to protect server bandwidth. If an external model tries to monitor a live inbox for a crucial update, those rate limits force it to check the inbox in batches. That delay creates a latency penalty. When that external model decides to act and attempts to write a command across two different enterprise services, it hits an authentication gateway. It must prove its permissions to both third-party servers before moving a single file. REMY bypasses this entirely. Internal execution allows for immediate context awareness, processing the incoming data and outputting the action at server speeds. Standalone competitors also hit severe context limits. Parsing years of long-term user preferences through narrow API bridges is computationally expensive and incredibly slow. In the race for proactive AI, external intelligence operates at a mechanical disadvantage. A deeply integrated, frictionless ecosystem consistently outpaces models waiting at the gate. While the theoretical architecture heavily favors an integrated ecosystem, the current reality of Project REMY is tightly controlled. Access to the agent is currently restricted. It exists as a staff-only version built into the Gemini application, kept strictly within Google's internal testing environment. Tech giants quarantine autonomous agents in closed, high-trust employee networks because giving software the power to execute actions carries massive operational hazards. There are no official public release dates announced. Analysts expect Google to outline further architectural details during their I/O developer conference, but deployment will be slow. This delay in public release is not driven by a lack of capability. It is a necessary testing period to measure the safety of allowing an AI to take unprompted actions. The systemic risk of proactive AI is straightforward. An agent that possesses the capacity to act autonomously also possesses the capacity to fail autonomously. In an automated sequence, a single execution mistake cascades outward. An error in step 1 creates immediate, compounding damage across every subsequent application. A generative model hallucinating an incorrect fact in a chat window is an annoyance. An action model hallucinating a decision and autonomously deleting a database carries severe penalties. Internal documentation explicitly warns Google employees to double-check REMY's responses. Proactive models process data faster, but they still lack flawless reasoning. To prevent an ecosystem advantage from becoming a massive liability, operators must maintain a human-in-the-loop constraint, requiring manual approval for high-stakes actions. As AI graduates from answering our questions to pulling the digital triggers, the true test for Project REMY will be proving that its autonomous actions are as reliable as its native access.